Hello, everybody, and welcome to this seminar. Today's speaker is Qingsong Wang, and he will talk about measure-theoretic Reeb graphs. Please take it away.
Right. Yeah. Thanks for the invitation and introduction. So today I'll be talking about a recent work called measure-theoretical Reeb graphs. This is a joint work with Ma and also Raghavendra Surya Ramusi and also Wang. Let's get started. So we will first introduce some backgrounds about the Reeb graphs. So for the Reeb graph, we are looking at a scalar field on a topological space. That is a topological space with continuous functions. And the Reeb graph is a quotient space that captures the variation of connected components of the level sets of the scalar field F. As for the equivalence relation that defines the quotient space, we say 2 points on the ambient space X is equivalent if they belong to the same connecting component of the level set. And here is an illustration of this construction, where we have X on the left-hand side, we have a function as the height function, and then for example, X and Y have the same connected component and have the same value, and they are connected in X. They will be mapped to the same point in the quotient space. And then the function F naturally induces a function on the graph by assigning the point in the quotient class as the point of the value for any representative in that class, because they all have the same value as they arise from this level set. And then therefore our Reeb graph is typically a one-dimensional graph alongside with a function that is a monotonic on each edge. And there are maps naturally can be defined between these Reeb graphs, which will be useful for our later study. Say we have 2 topological spaces with functions xf and yg. And we say a map between f and x and y is function preserving if the relation that G composite with phi equals f is satisfied, which is basically says that phi maps the level sets of f to the level sets of level sets of G. Therefore, by the relation about quotient maps, we naturally induces a map between the quotient spaces, which are the Reeb graphs. And that is phi tilde over here. And the phi tilde itself is a function preserving map with respect to the f tilde and g tilde on the Reeb graphs. And with this map, we can now define when 2 Reeb graphs are equivalent. We say 2 Reeb graphs are equivalent if there exists function preserving maps between them, and these 2 maps are inverse to each other. And here is some real-world application, which the Reeb graph is used to provide a one-dimensional skeleton of a complicated shape. For example, the Buddha on the left-hand side can be simplified to the as the right-hand side graph. All right, and the motivation for our work that is discussed today is to seek robust topological descriptors. The Reeb graph is a descriptor, and our new addition is to provide a more robust construction. So this arises from data science application where the ambient space is no longer a regular manifold, but rather constructed from samplings on the manifold where you only have the data points. And for the data points, depending on the noise or your specific setting, there are certain weights on the data points, which represents how much we trust this data or how important their corresponding features are. The conventional Reeb graphs do not take into a consideration of the data distribution. And typically, it could happen that a significant loop that is presented in the Reeb graph might be caused by a sparse set of data points, or lies in the region of low importance of the function values. And therefore, it could create a discrimination between the represented Reeb graph and the actual topology of the data. And therefore, our motivation is to capture robust topology in the data. And here is an illustrative example. So now we have the ambient space as on the left-hand side, where we have two loops, and our function is the height function. And if we simply construct the Reeb graph, it will look exactly the same as this ambient space. And now we have some heat map on this ambient space, where it represents relative density. So the density is higher on this side, but density is lower elsewhere. Therefore, even though we are seeing that the loop represented by alpha is larger than the loop represented by beta, but alpha lies in a region of low importance. Therefore, it is ideally for our Reeb graph to have a shrinked loop alpha to reflect the data distribution. But however, the conventional Reeb graph does not capture such distribution. And to formalize our goal, that is, we seek a general framework to construct Reeb graphs that incorporates the importance measure of data points. More specifically, we want to have the features or loops in the regions of low importance to be relatively smaller. And this construction should be stable with respect to the perturbation of function or the measure, which is requires a stability result in that direction. And our main contribution lies in the construction that is called locally smooth Reeb graphs, which adapts to the measure. And with this construction, then the two ideal properties will easily follow, both for the shrinking of loops in the lower importance region and also the stability. All right, so for the rest of the talk, I will first review the smoothing of Reeb graphs and the related concepts which motivated our construction. Then we introduce the locally smooth Reeb graphs and discuss its stability result. With the locally smooth Reeb graphs, we can construct our measure-theoretic Reeb graphs and also discuss its stability. And the key technical part lies in the stability lemma for locally smooth Reeb graphs, which we will spend some time to dive into that. And lastly, our framework allows an parallel extension to the Reeb spaces, which will be the last part for today's talk. All right, so let's first review the smoothing of Reeb graphs and the so-called interleaving distances. We will motivate the smoothing by the question of finding a measurement between the Reeb graphs. Suppose we have two Reeb graphs, which is both G and H are graphs, and F are functions. F and G are functions. And then we want to compare these two graphs. It should be discriminative, that is, it should have zero distance only when we have equivalent Reeb graphs. And it should be, this metric should be stable. That is, if we have some simplification of the Reeb graph, or if we have some perturbation of the function, it should not produce too much discrepancy in this measurement. And there are a couple of choices. There is the bottleneck distance, which you compute the sublevel set filtration and the resulted persistent homology of this function on the space of this on the graph, and then you obtain persistent diagram, and then you can compute the this bottleneck distance between the persistent diagram as a measurement of the discrepancy between these two graphs, two Reeb graphs. There's also the interleaving distance, which we will put more discussion in detail later. And also there is the functional distortion distances. And all these are largely equivalent up to some scalars. And we will focus on the interleaving distance, which is introduced by De Silva, Monch, and Patel in 2016. The interleaving distance is truly a metric on the space of Reeb graphs with some mild regularity conditions, so that these Reeb graphs are really graphs that are really one-dimensional, and also without repeated nodes. The construction is based on the notion of smoothing. The smoothing of Reeb graphs not only produces a nice interleaving distance, it also has a simplification effect on the Reeb graph, which inspired our locally smoothed Reeb graphs construction. All right, so let's look at the smoothing of Reeb graphs. So given a Reeb graph, G is a graph as on the first picture on the bottom, and we construct the product space with as G multiplied with an interval from negative epsilon to epsilon. So we have its pictorial representative as in the middle. Then the epsilon smoothing of G is the Reeb graph on the product space with the function f sub epsilon, where f sub epsilon extends the function f on G by adding a parameter t according to the location on each interval. And the last figure on the picture is the constructed Reeb graph, the epsilon smooth Reeb graph. So we use a convenient notation S for smoothing, S sub epsilon GF, to denote the epsilon smoothed Reeb graph. So already on this picture, we noticed that what happens, the smoothed Reeb graph looks very much alike the original graph, but with the loops are shrunk, and also some endpoints are extended. And these are exactly the two effects of the smoothing. And here is a simplified figure to illustrate these effects. So first, we have the shrinking of loops. So for example, the loop over here after smoothing will be shrinked. And the reason is that, for example, we look at 2 points, these 2 blue points, a priori, so we assume the scalar field f is the height function. So these 2 blue points are on the same level set. However, they are not connected in the level set. So therefore, you have 2 points on the Reeb graph. And then once you have the smoothed, once you look at these 2 points in the product space, you see that now they can be connected by a path, for example, this horizontal path. And therefore, with this product structure, you are making these points in the same level set are more connected. And therefore, for the smooth Reeb graph, you only obtain one single point, no longer 2 separated points. And this effect will have the will shrink the loops. Right. So additionally, we also see that these endpoints are extended. The reason is that, for example, previously the highest point is this top point, but with adding some epsilon, the highest point is now the previous maximum plus epsilon, and that is why you would have these extended points, extended ends. In particular, if you have this epsilon, how much you smooth your graph is sufficiently larger than the kind of half of the diameter of a largest loop, then every loop will be shrunk into a straight line, and then your Reeb graph will eventually be um, it should be a tree, be a straight line, and therefore, in particularly, it guarantees that for whatever two Reeb graphs you have, if you increase your smoothing effect large enough, these two Reeb graphs, these two smooth Reeb graphs will be the same, and they are the straight lines, so that the distance to be defined will be finite. Now let's define the interleaving distance that utilizes the smoothing of Reeb graphs. For every epsilon that is greater than 0, we define the so-called epsilon interleaving between two Reeb graphs as a pair of maps, phi and psi, so that the following interleaving type diagram commutes. So basically, phi maps G and F into the epsilon smoothing of H and G, and psi, on the other hand, maps H and G into the epsilon smoothing of G and F. And once you have these two maps, you can naturally have maps induced epsilon smoothing of GF into two epsilon smoothing of H and G. For this, as we can see, we want to produce some maps between the Reeb graphs. It suffices to find maps between the ambient spaces. And for the maps on the ambient spaces, we can simply utilize the map phi on the first component, and then extend it into the product space by fix an identity map on the second component. That's how the natural extension is constructed. All right, and then with this interleaving diagram, we can define the interleaving distance between two Reeb graphs as the infinement of epsilon, so that there exists an epsilon interleaving between GF and H, capital H and H. Sorry, it should be G. It's a typo. To be consistent with above. All right. Intuitively, the interleaving distance is the smallest amount of smoothing, so that gives rise to an interleaving of two given Reeb graphs. And the interleaving distance is stable with respect to the perturbations of the functions. That is the following result from the same paper that introduces smoothing. Suppose we have two Reeb graphs built from the same ambient space, but with different functions. Then the interleaving distance is bounded by the L infinity norm of the difference of the two functions. Additionally, with mild conditions on the Reeb graphs, the interleaving distance is truly a metric on the space of Reeb graphs. So basically, by the definition of interleaving distance, it will automatically satisfy the triangle inequality. So what is really needed to prove over here is that if you have 0 interleaving, then you truly have equivalent Reeb graphs. And as you can see, we define the interleaving using some infinement that is zero interleaving, meaning that you can interleave these two Reeb graphs as close as you want, but not necessarily that you can choose epsilon to be zero. That's why eventually you will need some regularity assumption to guarantee the equivalence between the two Reeb graphs. All right. And now with the introduction of the smoothing, we talk about our construction for the measure-theoretical Reeb graphs. All right, so let's recall our running example. So we have our ambient space as this this shape with three loops, 1, 2, 3, and we have our function f as the height function, so that in this case, the Reeb graph of this topological space X is exactly the same as it itself. However, we want to incorporate with the measure, so that we want to have the alpha to be smaller on the new Reeb graph. So the idea is that we identify that the smoothing of Reeb graphs not only produces an interleaving, a convenient interleaving distance, it also simplifies the Reeb graphs. But one issue with the smoothing is that it provides the kind of uniformed effects on this smoothing. That is not ideal because it is not adapt to the measure. And therefore, if we provide some local smoothing effect, where the smoothing factor is adapted to the measure so that we have a greater smoothing effect in the regions of low importance, then we can achieve our goals. And therefore, we have this construction of locally smooth Reeb graphs, and that is to smooth the Reeb graph with variable thickness. For the setup, we have some ambient space X with a function f. And now we have our function R, which is another function that is bounded and positive. And for convenience, we denote the supplement of this function as capital M. And the function will eventually be viewed as a local smoothing factor. And now, instead of producing a, now we find a generalization of the product space that is adapted to the local smoothing factor. That is, we first find the large product space where we second each point by negative m to m, but we do not take the full length of each interval at each point. We only need the interval, the subinterval that have its absolute value be less or equal to Rx, defined by our local smoothing factor. So therefore, our XR is a secant space where how much it is secant is defined by our function R. And then we can again naturally extend our function on F onto the space X sub R by taking the summation. And then our R smoothed Reeb graph is simply the Reeb graph on XR by the function F sub R. And when R is a constant function, this construction of locally smooth Reeb graph reduces to the epsilon smooth Reeb graph. And here is an example. So over here we have a locally smooth Reeb graph according to some local smoothing effect R. And then here is the constructed Reeb graph according to the function R. As we can see, on the for the loop on the top, it does not shrink too much because the locally smooth factor is small. But for the loop that previously was large, but since you have a larger smoothing factor, it will be shrunk so that these two have relatively the same size. And we also show that the locally smooth Reeb graphs are stable with perturbation of local smoothing factors. And that is, suppose you have the same ambient space and also this some given function on X. Suppose you have two different local smoothing factors, then the constructed two Reeb graphs are epsilon interleaved, where epsilon is the L infinity distance or L infinity norm of the between these two functions. And this is the key stability result for our construction. All right, so with this preparation, we can now introduce how we incorporate the measure into the Reeb graph construction so that we can achieve our previous goals. So recall the setup is that we have a metric space, and also we have a topological space X, and we also have a function F, and we have some probability measure on X. And we want to incorporate the measure so that we can find a suitable local smoothing factor. By suitable, we mean that the function should be larger or larger in the regions of low importance. And we have two settings for this choice of local smoothing factors. Suppose we have a metric on our space X, and then we use the so-called distance to measure, d mu m, introduced in Buchet, Chazelle, Aldok, and Cheny. Where mu is a measure and m is a positive number between 0 to 1, which is a parameter. If we do not necessarily have a metric on the space X, but we have some kernel functions, and then we can define, we can use the so-called kernel distance to measure a capital D mu k, where k is some kernel. And this kernel distance to measure is introduced in Phillips, Wang, and Zheng in 2015. All right, so without diving into the specific definition of these two functions, let me summarize the properties of these two functions, which will be used. So both d mu m and d mu k are positive functions on X, such that the function values are higher in the regions of low importance, which matches our need exactly. And these two functions are stable with the perturbation of measure. That is, if you change the measure mu to another measure, you can quantify this perturbation in little d or capital D by the perturbation of the measures. Specifically, we have these two following stability results, where the infinity norm of the two distance to measure functions is bounded by the two Wasserstein distance between the two measures, and the infinite norm of the capital D mu k for two different measures is bounded by the so-called kernel distance between these two measures. All right, so with this preparation, we can construct our measure-theoretic Reeb graphs, which means we use our d mu m or d mu k as our local smoothing factors for constructing the locally smooth Reeb graphs. We have an illustration over here. On the top, we have a setup where this space has higher measures on the left-hand side and lower measures on the right-hand side. And we choose distance to measure. And it results in a Reeb graph that fully eliminates the roof beta. On the bottom, we worked on a slightly different space where measures are lower on the left-hand side and higher on the right-hand side, and we choose kernel distance to measure and specifically use the Gaussian kernel in Euclidean space. And in this case, we are able to fully eliminate the loop alpha. So this is some illustration. And now we go back to the theoretical part. That is, we need to guarantee that our construction is stable with respect to the perturbation of function and measures. So over here, suppose our Reeb graphs are constructed on the same ambient space, but with possibly two different measures and also two different functions. And then the interleaving distance between the two d mu m smooth Reeb graph and d mu m smooth Reeb graphs are bounded by the infinity norm between these two functions, and also some scalar multiple of the two Wasserstein distance between the two measures. And therefore, the construction is fully stable with respect to the perturbation for both function and the measure. And in fact, the proof of the stability result is a consequence of two stability results. One is standard, that is the stability for Reeb graph with respect to the function on the same space. And another is the previously presented stability lemma for locally smooth Reeb graphs. And the proof is quite straightforward. You just use the triangle inequality so that you can have two cases. One is same space, different function. Another is same space, but different, same space, same function, but with different smoothing factors. And with these two stability results, you can prove the stability result presented for the d mu m smooth Reeb graphs. All right, and if you
Qingsong, could I ask
yeah,
a question if you go back a slide?
Yep.
So let's see. So x d mu m is a metric measure space.
Yep. X d mu m. So over here, it is a topological space. So the notation is that I'm viewing d mu m as a function that gives the local smoothing strength. Yeah. So
I see.
Yeah.
So X is a topological space, and that d mu m is like the local smoothing.
Yeah,
then,
exactly.
And then what about f d mu m?
Oh, that is so if we go back to the local smooth, so over here we extend the epsilon smoothing to local smooth. So therefore we first define this space, and we need to extend the function, and the d mu f is that function.
I see. So f was a function on x, but then you have the smooth version smoothed by this d mu. Yeah.
Exactly. Yeah.
And then so mu and nu are measures on x.
Yes, yeah,
I see.
on X. Yeah.
Okay.
Yeah, thanks.
Thanks.
Sorry, actually, since we're at the topic, I also had a question because I was wondering, I mean, on the slide before, I was wondering how come you only have like a sum of two? It looks very neat. And then now I understand that it's because of the triangle inequality. But how tight do you expect this to be? As in, because it seems like a very rough approximation.
Oh, yeah. Once we use triangle inequality, it's never too tight, but I believe we can construct some examples so that this inequality is not tight, but theoretically, I find it's difficult to improve it because after all, if you use interleaving distance, you need to construct maps between two different Reeb graphs, which by itself is not easy task if you have different ambient spaces. And yeah, so the conclusion is this might not be tight, and we may be able to find some counterexamples. But I believe a direct improvement is not easily clear to me.
Yeah, as in like I think like if you pick examples, you would probably find some where this thing is not tight, but it would be interesting if you could find examples where it is tight. I mean, I do not think that you would have tightness for all the spaces. I think that's impossible. But
I see.
yeah, like if you would find examples of your space X and then F, G and the two measures.
I see.
So that it is tight, then that would already make it tight in a sense. That would be definitely
Yeah, definitely. Yeah, I haven't think about that. I think if we are really aiming to find something like that, we could like make simplify this inequality a bit. That is, we make mu and nu the same, so that this term is eliminated, which means we only look for the tightness of the interleaving distance with respect to the function values. Where in this case, I believe it is tight. That is, if you have a simple interval, but with two different functions. And then in that case, I believe it will result in infinite distance between these two functions. Yeah. Yeah, thanks for the question. Yeah.
Okay, thank you.
Yeah. And if you are looking for the d mu k smooth Reeb graphs, it will also be stable, and the proof is very much the same as the previous one. All right, so more or less the most technical part is to prove this stability result for locally smooth Reeb graphs. So with some, so I will quickly go over that part. By the definition of epsilon interleaving, we need to construct a diagram like this and prove it is commutative. And in order to achieve this, we have like 3 steps. First, we will utilize an alternative construction of epsilon smooth Reeb graphs so that these epsilon smooth terms are much easier to work with. And with that, we will construct the maps phi and psi on the ambient space, which induces the commutative diagram. And lastly, is some diagram tracing for the commutativity. All right, so over here, I will talk about this alternative construction. So our Reeb graphs are constructed from some ambient space X with a function f, and the epsilon smoothing can be alternative constructed by first second the space X, and then extend the function f sub epsilon as fx plus t. And I'm saying this is an alternative construction because the previous construction in this case was to second the graph, second the Reeb graph, and then produce another Reeb graph, which is not easy to visualize. But with the alternative construction, all you need to do is you go back to the ambient space and then you second the ambient space and produce a Reeb graph. So you only need one Reeb graph or quotient map, which makes the visualization much easier. Right, and the second construction is much more convenient because it naturally connects with our locally smooth Reeb graphs. Right, and then with the previous alternative construction, our commutative diagram to find is something like this. We second the ambient space, even though the ambient space in this case is already these locally smooth spaces. And what we need to do is we need to find maps between these and also show they are commutative. And these are maps between Reeb graphs. And one way to produce such maps is to find function-preserving maps on the ambient spaces. That is, we go to the ambient space and construct some specific phi and psi. And this is the route that we choose. And on the next slide, let's define this phi and psi. I will just use phi as an example. So what happens over here is that we want to define a map from x sub r1, that is r1 smooth x, into r2 smooth x, and then multiply with some additional interval. In this case, we will utilize a construction that projects the real line onto specific interval. It is really a projection. That means if your input is within this interval, it will not change. If your input is outside this interval, it will be mapped to the closest point, either capital R or negative, either a positive R or negative R. And then the map phi is defined as from the x sub t, that is a point x, and also some t in the interval, and the interval length is less than r1x. And then you will try your best to map into x sub r2 by utilizing the projection. And for whatever does not fit, you will put it into the another component part, and that is the construction. And similarly, we can define a function psi, and we will need to prove that these two functions are function value preserving, and also it will produce a commutative diagram on the Reeb graphs. And that is, we need to prove two commutativities. One is that one is let me draw this. One is this commutativity diagram. Another one is so it is some diagram tracing to complete the proof. But what's interesting is that for the first item, it is directly commutative on the level of these ambient spaces. But for the item 2, it is not commutative on the level of ambient spaces. But fortunately, it is commutative on the level for the quotient space that is the Reeb graphs, which is exactly what we need.
Sorry, can I have a question here?
Yes.
So what does the trick? Like if it's simple to explain, what is the difference between the ambient spaces and the Reeb graphs that actually lets you achieve your goal?
Yeah. So what happens is for the item 2, if we simply evaluate left-hand side and right-hand side, it will typically not be the same point in the ambient space. But luckily, if you look at the Reeb graph, you will find that they not only have the same function value, but you can find a path in the level set connects these 2 points, so that they represent the same point on the Reeb graph. And that's why we will have a commutative. That's how we can have a commutative diagram at the Reeb graph level, which is what we need. Yeah.
So did I understand it wrong, correctly? In a nutshell, it's path connectivity. So you can
Yes,
have two different points, but they are path connected, and
yeah,
that's
they
why
are exactly. Yeah.
Okay, great,
Exactly.
thank you.
Yeah, thanks. All right, so that is the technical part, but I believe our contribution was mostly the construction. All right, and lastly, there is an extension to the Reeb space, which is quite parallel. And for the Reeb space, it is a higher dimensional generalization. For the Reeb graph, which you don't have a single variable function. I mean, your target space is no longer one-dimensional, but d-dimensional, so that you don't necessarily have a graph as your Gaussian space, but it will typically d-dimensional with some mild regularity conditions. And our locally smooth Reeb graphs construction and also related stability result can be extended to the Reeb space once you prove all these following ingredients, that is stability of Reeb space with respect to perturbations of functions, equivalence of the two constructions of epsilon smooth of the Reeb space, whether you smooth the ambient space or you smooth the resulted Reeb graph, Reeb space. And you construct similarly the locally smooth Reeb spaces and how it adapts to the measure, and then you can prove the stability for the locally smoother Reeb spaces, and you can work it out for the Reeb spaces. And as a conclusion, the motivation for this project is to find robust topological descriptors, so that the Reeb graph construction can be aware of the measures. And our construction utilizes local smoothing, which nicely provides simplification for these loops, and also being stable with respect to perturbation of functions and measures. And in our paper, we additionally have some other parts that is so-called range integrated Reeb graphs, which takes care of measure on the range of a function, which is basically a rescaling. But nicely, it is also stable. And for ongoing projects, we are seeking some applications for visualization to work on more real-world data sets. And yeah, and thank you.
Thank you very much. Before we get to questions, please, everybody, let's unmute yourselves, ourselves, and clap for the speaker.
Thanks.
All right, thank you very much for the great talk. It's time for questions.
I had a question, Qingsong. So I think like one example you have in mind is maybe X is an annulus, right? And then one measure is like a uniform measure on the central circle in the annulus. And then another measure might be you have like a finite sample of points in the annulus, and you have you know, Dirac deltas at each of those points, right? So the question is, in those examples, like X was the annulus, but the measures, like the measure on the circle or the measure on the finite number of points, was only supported on part of the annulus. So do the functions still need to be defined on the entire annulus, or yeah?
Oh, I think right now in the current work, it's still working in a nice ambient space that is continuous. But we have different measure importance on different parts, and that will affect that will have effect on the size of the loops. And And in real application, we will need to consider sample points, as you said, like data measures. And in that case, yeah, we will need to find a good ways to construct or approximate Reeb graphs using samples. And in that case, we might use mappers, or we can first construct Reeb's complex and then construct the Reeb graphs. So that adds additional layer of difficulty to the sampling things. So right now, the theory as in this paper only mostly considers continuous ambient spaces.
But you could have a continuous ambient space like the annulus and a function defined on the entire annulus, but then your measure is just a finite sum of Dirac deltas.
Oh yeah.
Yeah, you can handle that. I see.
I see. Yeah, you're right. It can be handled in this work. And
I see.
Like contributed to the nice property of this distance to measure functions, right? The functions.
Right, I see.
Yeah.
I see, but this doesn't like directly handle the case where the functions only defined at finitely.
Yeah. For that, we will need some good results that can approximate Reeb graph by using only samples, which is kind of difficult.
This is the framework building towards that.
Yeah, exactly. Yeah,
oh, cool. Very nice. Thanks.
I actually had a question since you're on this slide. How did you choose the R? So this varying thickness parameter in these two pictures, in case you know?
Oh yeah. So in these two pictures, so first we already have two different setups as the measures. And this serves as a purpose to show that both distance to measure and current distance to measure works fine. So I believe what happens is that on the top we used distance to measure, and for this we already have some relative density comes from a measure, and we used the Euclidean distance. I'm sorry. I believe it was used the distance on the graph, and then with this distance we can define the distance to measure, and use it as our local smoothing factor, which determines the width at each point, and that's how this Reeb graph eventually is constructed. And for the distance to measure, there is a parameter m, and so that to determine how much you want for the for a local neighborhood to have that much of mass. But I'm unsure about exact math we used. And at the bottom, it was using the kernel distance to measure, and the kernel was a Gaussian kernel, and once you choose the Gaussian kernel, there's no much parameters, and I believe that is the local smoothing function used in the for the bottom part. Yeah.
Okay, thank you.
Yeah, thanks.
Are there any more questions? Tomoki, go ahead.
Can I ask a question?
Yes, go on.
So, do you assume any regularity condition on the local smoothness factors? I mean, absolute unity on the measures or something like that?
So let me think. So the most regularity is for the space X and F, and for the local smoothing, even if for the local smoothing factors that determines the bandwidth, even if you have something really messy, but as you can see, our construction of this X sub R is a subset of this interval, and eventually this X sub R deformation retracts to the X, so that it will not produce bad loops, because this X sub R always deformation retracts back to our X. So in that sense, even your local smoothing factor R is not good looking, but we are still truly smoothing out the loops built on X. So the short answer is no, we do not assume additional smoothing regularity assumption on the R, and I believe it will not cause problems. Yeah.
I understand.
Yeah. Thank you.
Are there any more questions? Okay, this does not seem to be the case. So thank you very much again.
Yeah, thank you.